Okay, so this is the last scenario for doing hypothesis testing on the mean, right? So we consider the scenario where we either know the variance of the population or we have many samples, right? So the case that we don't have many samples and we also don't know the variance involves the use of the t distribution, such as quite similar to the confidence interval case, right? So we basically, the test statistic that we compute is t, right? And the equation is exactly the same as the equation for confidence interval, right? And then the rest is quite similar to the basically previous case for the z distribution. So if we compute t, if it's more than, our t of alpha divided by 2 and n minus 1, or less than t of alpha divided by 2 and n minus 1, we reject the null hypothesis, and that means that, so this is minus t of alpha divided by 2 and n minus 1, and this is plus the same thing, right? So if we are here or here, in these two cases, we reject. And that's the case for the alternative hypothesis being double-sided, right? And if it's one-sided, again, same as before, right? So if it's one-sided, then it has to be t has to be more than t of alpha and n minus 1, right? So I would say nothing is new with this slide. Everything is, either same as before, either same as the hypothesis test or the confidence interval, right? So let's look at one example to see how this actually works. 15 drivers were selected at random and their coefficients of restitution measured. Calculate if there is evidence with alpha equal to 0.05 to support a claim that mean coefficient of restitution exceeds 0.82, right? So since what we are interested in is, this coefficient exceeding 0.82, then the alternative hypothesis is one-sided, right? So we say that H1 is mu is more than 0.82. And of course, H0 is mu is equal to 0.82. So the first thing that we have to do from these, these 15 measurements is we have to calculate X bar and S, right? So we see that we don't have sigma, right? So sigma is unknown and n is, less than 40. And because of these two, we have to use the t distribution. Right? Any questions so far? Okay. So basically all we have to compute is the test statistics, which is X bar minus mu, which is 0.82, divided by S, divided by square root of n. What is n? For n we have to count. So it's a table of 3 by 1, 2, 3, 4, 5. So 15. Right? So that's it. This is all we have to compute. And we have everything. We have X bar and we also have S. Right? Any questions so far? Yeah.
Can you repeat again the conditions for using the t distribution? Is
Sure.
it also always when the population is small?
Yeah. So basically, both of these have to hold for you to use the t distribution. First of all, you should have few samples, right? So if you have more than n samples, for sure you have to use the normal distribution, not the t distribution, right? So this condition is satisfied, and another condition that must also be satisfied is that we should not know sigma of the population, right? And we don't know. All we have is 15 measurements, right? So if either of these two were not satisfied, then we had to use the Z, the normal distribution. So for example, if sigma was known, or if n it was more than or equal to 40, in these cases, we had to use the standard normal case. Any other questions? Okay. So as you can see, I think these are very easy. Hypothesis testing is really easy. All you have to identify is whether you have to, if it's for the mean, exactly the same as confidence interval, right? So you have to see what the question wants. Does the question want mean or the question wants variance, right? So we will cover variance as the last topic in the next few slides. If it wants mean, do you know sigma or is n large, right? If either of those are satisfied, then standard normal. Otherwise, it's the t distribution. So if you practice, in my opinion, it's impossible to make a mistake. Okay. So we compute, we plug in, right? We had x bar, which is 0.83. We plug into the equation, and the t value that we get is 2.72. Right? So one thing to remember is that in this equation we have n, but in the table we have to look for n minus 1, right? That's the degree of freedom, right? So we had 15 numbers, so we have to look at row 14, which is for 15 minus 1, right? So for 2.72, right, we don't, usually, when you compute t, almost always, you don't see the exact t in this row, right? So this table has different t's, for example, t of, 0.25, t of 0.69, and so forth, right? And almost never you see this exact number in this table, right? Because these numbers are quite sparse, right? So all you have to do is you have to identify the range, right? So 2.72 is here, is between 2.62 and 2.97, right? And that means that alpha is between these two numbers, right? So basically you will say that alpha or p is between 0.005 and 0.01. Okay. Yes?
We choose 14 because it's a one-sided.
No, 14 has nothing to do with one-sided. You always have to look at n minus 1 here, right? Regardless. So if I go back, where's this? If I go back, in all cases, so this is for a two-sided hypothesis test, and these two are for one-sided, right? And all of them here, they have n minus 1. Right? So basically the test, basically what you have to compare to is, t of alpha divided by 2 and n minus 1. What actually changes is this guy. Is here we have alpha divided by 2 for two-sided, and here we have alpha. That's what changes. N minus 1 is always n minus 1. Other questions? Okay. All right. So the conclusion that we make is that from this table with the t distribution with 14 degrees of freedom, T0 equal to 2.72 falls between 2.62, for which alpha is 0.01, and 2.97, for which alpha is 0.005. And therefore, the p-value is between these two numbers, 0.01 and 0.005, which means that it's less than 0.05, right? So this is the critical value. If it's less than 5, if there is less than 5% chance of making a mistake, you reject the null hypothesis, right? So we reject H0 and conclude that the mean coefficient exceeds 0.82, right? Or you don't need to, say that for this course, but basically this analysis means that we can also conclude the following. We reject H0. The probability that we reject H0 by mistake is less than 0.01 or 1%, right? So that's what it means when we say p-value is less than 1%. That means that the probability that we reject H0 by mistake is less than 1%. And that's a very reasonable probability, right? If there's less than 1% chance that you're doing something by mistake, I think that's a reasonable chance. Any questions? Okay. Right. So the final topic of this course, it's the final topic. There's nothing after this, is hypothesis testing and the variance, right? And if you studied the confidence interval chapter, this is exactly similar to confidence interval for the variance, right? So the test statistics, again, is the chi-squared distribution, right? So here, basically, what we are interested in is we have a bunch of measurements, right? We have n measurements or n samples. And we want to find out some, not confidence interval, we want to find out whether the standard deviation of the population is equal to, something that we think is the standard deviation, right? Is equal to sigma 0, right? So basically what we have is from these measurements, we calculate S, right? And based on S, we want to decide whether sigma, for example, is sigma 0, right? And this is our null hypothesis, right? So we have a bunch of measurements. From these measurements, we estimate S, which is the sample variance or sample standard deviation. And from this, we want to conclude whether the null hypothesis that sigma of the population is sigma 0 is correct or not, right? And as you have probably guessed, we have to use the chi-squared distribution, right? So this variable follows the chi-squared distribution. Okay. So that was the case for two-sided. For one-sided, we have the exact same scenario, right? So our H0 is sigma is equal to sigma 0, and our alternative hypothesis is either is more than some sigma 0 or less than some sigma 0, right? And in this case, we reject the null hypothesis. So if this is the chi-squared distribution, remember chi-squared distribution is always positive, right? So if this is chi-squared of alpha and n minus 1, if we are here, then we reject H0, right? And for the bottom case. This is x squared of 1 minus alpha and n minus 1. Again, if we are here, we reject h0, right? So it's for this case, and this is for this case, right? Quite similar to the mean. Any questions? Okay. So yeah, you can see actually all of the cases here, right? So this is if we want to test whether it's more than something, less than something, and this one is the two-sided case. So this one is two-sided. Any questions? Okay. So let's look at an example. An automatic filling machine is used to fill bottles with liquid detergent. A random sample of 20 bottles results in a sample variance of fill volume of S squared is equal to 0.015. If the variance of the fill volume exceeds 0.01, an unacceptable proportion of bottles will be unfilled or underfilled or overfilled. Is there evidence in the sample data to suggest that the manufacturer has a problem with underfilled or overfilled bottles? Use alpha equal to 0.05 and assume that the fill volumes follows a normal distribution, right? So because the question says we have problem if variance exceeds 0.01, this is a one-sided test, right? And by the way, that's always the case, you know. Always a large variance is a bad thing, and a small variance is a good thing, right? That's almost always the case. Whatever you do, you know, you want to decrease the variance. Any questions about the problem statement? Okay. And by the way, even in financial markets, you know, if you want to look at the return of something, it's not just important how much the expected value of your return is, right? How much you are expected to win. It's always normalized by the variance, right? So if something is expected to give you a little bit back, but is guaranteed, it's usually preferred to something that's expected to give you more back, but it has a huge variance, right? So financial analysts always take that into account, right? They try to maximize the expected value of the return while minimizing the variance, right? Always variance is a bad thing. We don't want, you know, large variations, right? So here, for example, if the variance is large, some of the bottles will be overfilled or underfilled. So the question is related to variance, and because of that, we have to use the chi-squared distribution. So our test statistics is x squared of 0 is, according to the equation, n minus 1 times s squared divided by sigma 0 squared. And the question says use 0.05, right? So x squared of 0.05 and 19. So we look at the table for 19 degrees of freedom here. And 19 is because we have 20 samples, right? So n minus 1 is 19. So here we look at x squared of 0.05 and 19. So 0.05 is here. So the number will be 30.14. Right? So basically 30.14 will be our threshold for rejecting the null hypothesis, right? And the x squared that we calculate is 29.05 0.07, right? So if I draw, this is what's going on. So this is 30.14, right? And if we are here, we reject. Or in other words, this area under the curve is, from this guy, is 0.05, right? And the chi0 that we compute is 29, so it's here, right? So should we reject the null hypothesis, or we cannot reject the null hypothesis? What is it? Yeah, exactly. We fail to reject the null hypothesis because it's not, we don't have strong evidence to reject the null hypothesis, right? In other words, if we reject the null hypothesis, there's a chance of more than 5% of doing that by mistake. And that chance is unacceptable, more than 5%, right? So because of that, we say it seems to be okay, right? So we say that variance is not too high, or the data doesn't suggest that the variance is too high. Any questions?
Because last time, if it was like farther right past the 0.5, then the numbers like the probability is smaller. So I thought you said like the odds of failing to reject is lower. Now we say that we accept it.
No, we don't say we accept. We say that. So basically, if we want to write down what conclusion we make, we say that we fail to reject H0, right? And the reason for that, I'm not going to write that down, but the reason for that is that if we reject H0, the probability of doing that by mistake is something between 5 and 10% between these two guys, right? And that's a large probability of error. And because of that, we don't reject H0. We fail to.
So why is why did you say the variance is acceptable? I thought like that would mean like the variance would be unacceptable.
So what is H0? H0 says that sigma squared is 0.01, right? So we don't reject it. It means that sigma is probably 0.01. Right, so we don't reject has two negatives, right? We don't reject has two negatives. It essentially means we accept it. Okay. So since x squared is 29 and is less than the threshold, we conclude that there's no strong evidence that the variance of field volume exceeds 0.01. So there's no strong evidence of a problem with incorrectly filled bottles, right? So likely we are not going to have a problem. Any questions? Okay. So what we did is basically summarized here, right? So we find basically, so this is the case for the two-sided case. We find these thresholds that we need to reject, right? And probability of each one of these is alpha divided by 2. And if x squared that we compute is more than this guy or less than the other one, we reject. And again, here, exactly like the case for confidence interval, note that here we have alpha divided by 2, and here we have 1 minus alpha divided by 2, right? This is different compared to the t distribution, right? And the reason for this is that chi-squared distribution is not symmetric, right? Because it's not symmetric, we have to look at the values for 1 minus alpha divided by 2 and alpha divided by 2. For the case of, for example, t distribution, the nice thing about the t distribution is that t of alpha divided by 2 and n minus 1 is equal to t of basically, so for t distribution, if this is 0 and these two are symmetric, this probability is always equal to this probability, right? So all we need is to compute one of them, the other one is the negative of the other one, right? But in this case, that's not the case. We actually have to look at the table for both this boundary and for the other boundary. So this is exactly the same as confidence interval. So we will do a few samples, I'm going to do a few suggested problems, and we will see basically that similar to confidence interval, we have to look at these numbers in the table. Any questions? Okay. So that's it. 9.42 is not a part of this course, so there's nothing more to cover. I wanted to mention something about your project, right? This would be quite interesting to mention in your project, to think about this, right? So this is a true story that I want to share with you. So after World War II, the US military wanted to reinforce. How many of you have heard about this story? This is a famous story. 2, 3? Okay. So don't say the answer, right? So I want everybody to think about this problem, because I couldn't think of the answer, right? Maybe because I was shown the answer quickly. So this is a true story, right? And the story is that after, during World War II, the military wanted to reinforce airplanes, right? Find out where the airplanes are vulnerable and where they are getting hit. And they wanted to reinforce those parts of the airplane so that, they don't get damaged, right? So they basically, let's say, took pictures or recorded where these airplanes are hit, right? So these are the areas where the airplanes are hit, right? So after they finished a mission, they came back, let's say, to wherever, the US or, to a Navy ship. And after they came back, they looked at the damage that they sustained, right, from the bullets, right? And, they wanted to reinforce these areas, right? They said, oh, these areas, the steel needs to be, or the aluminum, whatever is used, needs to be reinforced because they get hit a lot, right? And they had statistician from University of Columbia University on, as sort of like a consultation, right? And the statistician pointed out that this is exactly the opposite of what you wanted to do. This is incorrect. So you do not want to reinforce these areas, right? So they pointed out that the conclusion of the military is wrong. But can you think of why this basically conclusion is wrong? That it is a bad idea to reinforce these areas. Yeah.
The areas you want to reinforce are going to be the areas where damage would have caused the airplane not to return.
Exactly, yes. So that's exactly the answer. So basically what the statisticians argued is that these planes were hit in these areas and they still managed to return, right? The pilot didn't die, right? So that means that, these areas actually can be damaged without loss of the human or loss of the airplane, and they can still return, right? And the areas that should be reinforced are exactly the areas where you don't see any bullets, because if the airplane was hit at that point, it probably never returned, right? Another famous case of these is, so this is called bias from sampling, right? So you have a bunch of, remember that when we have, we often to find out to infer properties of a population, we have to sample from that population, right? And the military thought that they have a large enough sample of the planes that were, involved in the war, and they said that, all of the samples that we have, these are the areas that are hit, and the plane is damaged, and because of that, we have to repair the plane. So let's reinforce those areas, right? So this is a problem in sampling, right? When you're sampling, your sampling is actually biased to, to some certain part of the population, right? Another famous problem of this are clinical trials, right? So in clinical trials, unfortunately, most of the time, white male are enrolled in clinical trials, right? So if a drug works well, it works well for white male, but it's not guaranteed to work well for women or for other ethnicities, right? So there is again a problem with with clinical trials, and that's something that now everybody knows, and they have to correct for that, right? So when you develop a method, you have to correct for biases that you see from your sample, right? So another area, which is my own area, is deep learning, and we have a lot of clinical data, right? And unfortunately, these clinical data again are collected, let's say, images of like the lungs or the brain, right? These images are usually collected at few geographic locations, right? So all of the public data sets are usually from a few large hospitals that were large enough to have a research team to release the data, right? So that means that whatever method you're developing, you're actually developing for those people, whose data are actually shared, right? So if you're collecting data for your project, you can think of the ways that your samples could be biased, right? And you can mention in your report that, I think, and by the way, this is called the survivor's bias, I think, right? And this is usually quoted as like, so like you see like these quotes from famous CEOs that, yeah, I dropped out of the college and, I dreamt big and, like things that, like successful CEOs say, but that's also called the survivor bias because you're only looking at people who, dropped out of college and actually succeeded. There are so many of people who drop out of college and don't succeed, right? So that's also, like if you just follow, what super successful people did, it's not guaranteed that you also be successful, right? Because you only hear the stories of the people who succeeded. Right? Another famous case was some military, I don't remember, I think it was British military, had helmets, right? So they, for the wars, in one of the wars, probably World War I, they designed helmets for the soldiers to put on so that, it protects the head from sharpeners and from projectiles, that come to the head. And after the soldiers started wearing those, the hospitals, sort of filled with brain injuries, right? And, again, some military, contractors said that, oh, these helmets are a bad idea because, since we introduced them, we have many, many more injuries, brain injuries, right? And then, wiser people realized that it's good that we have injuries. These people would have died if not because of those helmets, right? So these are things that you can actually consider, like you can mention, you can think about how your samples could be biased, right? I think in the project report, I mentioned another case that like during some election, the results, or actually our case, during the Trump election, everybody was saying that, Hillary is going to win with a chance of 95%, right? But the thing was that people who were, people who participated in those polls, the ones who answered were actually more likely to vote for Hillary. The ones who were, angry about the system, they just didn't participate in the polls, right? Or like they were maybe like ashamed of saying that I want to vote for Trump, right? So they didn't say what they wanted to vote for, right? And that's why, all of the polls were wrong by a huge margin, right? So bias in sampling is always a big, big problem, right? Okay. So now I will review a few concepts that, I think are worth, reviewing, and then we will solve sample questions from the book, and then some sample final exams. So we already covered covariance, and are there any questions? Yep. Yeah.
I just wanted to know, is it cumulative? So everything since the beginning of the term, or just since the midterm?
Yeah, no, everything will be in the final exam because, because your grade may not depend on the midterm exam, right? So it covers everything. Other questions?
How many classes do we have left?
What is it?
How many lectures do we have left?
Oh, we have 2 next week and then 1 after that.
And all are going to be with you, right?
Yeah, so the 2 lectures next week are going to be with me. The one after that, I'm going to attend the conference. So there's 3 sections of this course, right? And a prof teaches those other 2 sections. So he agreed to teach, in this section also on Monday. So the very, very last class, the other prof will teach.
And on that last class, will that prof be teaching here?
Yeah, here. Yeah, good point. I should tell him where the location is. I assumed he will look up, but I should tell him. Yep.
Are you going to post solutions to the final exam?
Yeah, I will. Yeah, so that's one of my plans. So hopefully next week I already posted, I think, 2 final exams, right? I will post the solutions on Moodle. Yeah.
What's the weight of the final exam?
What's the date?
The weight,
Oh, the weight.
since you put the midterm on 25, so is it going to be 45?
I don't remember. Sorry, I don't remember the weight. It's in the syllabus, right? So there are 2 schemes that your grade could be calculated on: scheme A and scheme B, and the weight of the final is different in those 2 schemes. What is
I
it?
know, but because the midterm was supposed to be on 20, and then it was on 25.
Oh, that's not important,
So you're just going to convert it to 20.
Yeah, of course, yeah. Other questions? Okay, so I think this graph is very important, right? So here, the data that we had, we have 2 variables, right? And whenever we have 2 variables, think like it's a little bit difficult to imagine things, right? So what you could think of is X is like the weight of, some samples that we have, and Y is the height of a few, like those samples, right? So these are 2 different random variables, right? And we have the probability of each co-occurrence, right? So for X equal to 0 and Y equal to 0, the probability is 0.2. So like the way to write actually what picture represents would be probability of X equal to 0 and Y equal to 0 is 0.2, right? Or probability of X equal to 1 and Y equal to 1 is 0.1, right? ... Right. So from basically these PMFs, so this is called PMF, probability mass function, and this is a joint PMF because we have X and Y, we have 2 random variables. So from these we can calculate covariance and correlation, right? So I'm not going to go into details of how we did it because we already did this, and you can look at the video if you want. It is recorded. I hope it's not one of the lectures that I didn't record. I think I missed recording on 2 lectures. So the covariance value that we get is 1.2, right? And remember, covariance can be any number from -infinity all the way to +infinity, right? And the nice thing about correlation is that it is between -1 and 1, right? So correlation is essentially the same thing as covariance. The only difference is that correlation is normalized covariance, right? Meaning that it's always between -1 and 1, right? And what that means is that numbers actually have meanings for correlation. For covariance, numbers don't usually have any meaning, right? So a covariance of 1.2, we don't know whether that's a high covariance or a low covariance, right? But once we normalize it and convert it to a correlation, now actually this number has a meaning, and since it's quite close to the maximum number correlation can take, we can say that X and Y have a large correlation. And we can also see that from the graph, right? We see that generally as X increases, Y also increases. Right? So we also, another concept that's quite related to correlation, but is not the same, is independence, right? So we saw that if X and Y are independent, therefore, can we conclude that covariance between X and Y is 0 if they are independent?
Yeah.
Yes, exactly. Therefore, covariance of X and Y is 0. Right? And I encourage you to try to prove this. This is not difficult. Right? I believe we did prove it during the lecture. But the other way around is not correct, right? If the covariance or the correlation is 0, so if covariance is 0, then correlation is also 0, right? So if covariance is 0, it's not guaranteed that those two random variables are independent. They can still be dependent, but not correlated. Any question? Yep.
So you conclude that they're independent only if covariance and correlation is 0.
So to show independence, that's a good question. So basically, let's say that your interest is to test whether so basically you want to test R. So are X and Y independent, right? So if you want to test whether X and Y are independent, it's not a good idea to test whether correlation is 0, because even if correlation is 0, you're not sure that they are independent or not, right? So to show that X and Y are independent, what you have to do is, does anybody remember what we have to do?
It's not fxy is equal to fx.
Exactly. What we have to show is, we have to show whether f of X and Y is equal to f of X times f of Y, right? So that's how we show independence. And to show this, first you have to calculate f of X, and then you have to calculate f of Y, and then you have to multiply them, right? Any other questions? Okay. Right. And I presented these results. I really like these because this is one example of how you can use the material that you learn in this course to things that may not be related to statistics at all, right? So here we have a large file of 4-digit credit card passwords, right? And here what this person did is that he created, so this is called the joint PMF, joint probability mass function, right? So the first, so if we call this axis x-axis, and if we call this axis y-axis, he defined x-axis as the first 2 digits, and he defined y as the second 2 digits, right? And then colors here represent probabilities. So bright colors show very large probability, and dark colors show low probability, right? So we see, for example, that from this graph, we see that many people picked passwords which have the same X and Y, right? Meaning that passwords such as 8585. Okay, so from this graph, in fact, you can find the correlation between X and Y, right? Because we have all the probabilities. So similar to this, result, we could actually find the correlation between the first two digits and the second two digits of credit card passwords. Any questions? Okay. All right. So we covered t-distribution and the normal distribution, right? I showed you different t distributions and different normal distributions, and you saw that as the degrees of freedom were increasing, students' t distribution was getting closer and closer to the Gaussian distribution or the normal distribution, right? You can also see that in numbers from the tables that are provided in the book and also in the crib sheet, right? So let's look at that. So, for example, for a degree of freedom of 60, right, it means that we have 61 measurements, right? We see that basically the t-value here is 2, right? So that means that if I have a t-distribution with n equal to 61, then this is 0, this is 2, then this area under the curve, what is this area? 0.025, right? Is basically this number here. And if we look at the counterpart in the Z, in the normal distribution, we see that the number here is 1.96, right? So 2 is quite close to 1.96, right? And that's why for degrees of freedom more than 40, we just use the Z distribution, right? Because the difference would be the difference between 2 and 1.96 here, 1.96, right? So if I draw here, then for the normal distribution, if this is minus 1.96, then this area under the curve is the same area, 0.025, right? And we see that as the degrees of freedom increases, so when we go from 60 to 120, we get even closer to 1.96. So this becomes 1.98. And then when we even increase to a very large number, it becomes exactly the same as the normal distribution, right? 1.96. And we see that for smaller numbers, they are very different. For example, if we only have 4 data points, then the number is a very large number, is 3. Right? So for small numbers, t-distribution and normal distribution are very different. For large numbers, they are the same. Any questions? Okay, so let me cancel this. Okay. So we can also look at other numbers, right? So here we have a probability of 0.05, right? So here the probability is 0.05, and also here is 0.05. Again, we see that for 61 data points, the number that we have is 1.61, and here also is, is 1.67. Here is 1.65, right? Quite close, right? And when we increase n from 60 to 120, then it becomes 1.66, which is quite close to 1.65 here, right? We can also look at other numbers, for example, here. So this means that, so if I draw this one here, for the t distribution, so this number is 0.254, and this area under the curve is 0.4. So that means almost half of the area, right? Close to 0.5. And here, the associated number is, for the z distribution, is 0.25, right? So quite similar, right? So one interesting thing from this comparison is that close to the peak, right around here, the distributions are almost the same, right? Because these numbers, right, even if you look at 3, right, even if we have 3 samples, this is 0.27, and this is 0.25, right? So the difference is in the second decimal point, right? So for basically large probabilities, which means around 0, the two distributions are quite similar. The only difference between them is at the tails, right? So the t distribution is said to have long tails, right? So meaning that it doesn't, so if this is the t distribution, the normal distribution attenuates to 0 much faster than the t distribution, right? And that's why, these numbers, as we move here, for example, 0.1, these numbers are more different compared to the normal distribution as opposed to, these numbers, for example. Any questions? Okay. So, yeah, we already did this one. Surprised, actually. I thought I deleted this. Okay. So let's look at one example. A new engine manufacturing technology is proposed for reducing the pollution. 10 engines are sampled, and average and STD of pollutions are respectively 17.17 and 2.98. The old method had a mean emission of 20 ppm. Does the new technology generate less pollution? Right? So we can basically summarize what we read. So the null hypothesis says that mu0 is 20, right? And the alternative hypothesis, what is it? What is the alternative hypothesis? It's not 20, or it's more than 20? Or less than 20, right? So basically the question says we are trying to reduce the pollution, and that's why we generated this new, engine manufacturing. So mu1 will be, will be less than 20. Right? So we want to decide between these two. We want to see whether the null hypothesis is correct or the alternative hypothesis is correct. Right? So we read the question, and the question says x bar is 17.17, and standard deviation of those samples is 2.98. So this is very important to write. S is 2.98, right? So note that this is S, it's not sigma. It's S because it's from the samples, not from the population.
Does it say it more because here it could be a bit ambiguous whether it's a standard of pollution.
Yeah, so
think of that as the entire pollution.
You mean about this, about S?
Well, the way it's written, yeah. In the question, it says standard of pollution.
Yeah, so I thought of the same thing, but after you read it the second time, the question says 10 engines are sampled, right? And then this is follows, and the average and standard deviations, right? So you're right, it doesn't say specifically that and sample and standard deviations of those 10 samples, are these, but I think this is the most, reasonable assumption to make when it immediately says that the average and STDs are this and this, right? Okay, so since, and n is 10, right? So since n is small and we don't have sigma, we have to use the t distribution, right? And that's it. At this point, we are done. Right? So basically, all we have to do is we have to calculate t0, which is x bar minus mu divided by s divided by square root of n. And we have everything, right? We have 17 minus 20, 2.98 square root of 10. That's it. Any questions so far? Yeah.
Just like, I didn't understand when we use T0 or Z0 and when we have to calculate, for example, alpha or beta.
I see. Yeah, so, that's a good question. So the question is, when do we calculate T0 and when do we calculate T of alpha, right? So T0 is computed from, the samples, right? So T0 always is related to the samples that you have, right? So it basically comes from X bar and so forth, right? And then we have to compare T0 to T of, so in this case, it's a one-sided, so we have to compare to T of alpha and n minus 1, which is 9, right? So after we compute this number, whatever this number is, we have to compute it to this other number, compare it to this other number, T of alpha and 0.9, and the question doesn't say anything, so we have to assume alpha is 0.05, right? So T of 0.05 and 9, right? And this number comes from the table. I think we had the table in the previous slide. Oh, we don't have for 9, right? So we have to look at row 9 here. So we have row 1, 2, 3. We have to look at row 9, and then for 0.05, right? So the number is going to be something between these two, right? So around 2. Any questions? Okay. Okay, so if we compute this number, actually let me start again so that we get rid of the annotations. So t will be minus 3, and minus 3 is a very small number, right? So my hunch is that we reject the null hypothesis, right? Meaning that the new engine is actually better, because minus 3 is a very small number, right? But let's continue to make sure. So from the table, actually, yeah, still a small number, right? So from the table, we see that for 9 degrees of freedom, 3 falls between these two guys, right? So that means that alpha or P, probability of type 1 error, is going to be between these two guys, right? So less than 0.005 and more than 0.01, right? So it's less than 0.05. So that means that we reject H0. Yep.
Do we always take, for example, here we assume that the value of alpha is 0.05, right?
Yep.
But then we always take the value in the table. We always take the value before, right? So, for example, if we had a different value of alpha. Then we'll take, for example, say the alpha will be 0.025. Then we'll take 25 and.
Oh, no. So let's say that the question said, does the new technology generate less pollutant engines? So what do you want to set alpha to?
Okay, so let's set alpha for a different number because.
A bigger number or a smaller number?
Smaller number.
Smaller number. So let's say set alpha to 0.01. Instead of 0.05, let's say we are setting alpha to 0.01, right? So, and that is, now becoming more common, in a lot of fields, people want a smaller p-value, not a p-value of 5%, for example, a p-value of 1% or even less than 1%, right? So this is not uncommon to say that set alpha to 1%, right? Nothing changes because in the table, we looked for -3, right? So I'm here because of -3. I didn't look at these first. I looked at these numbers first, right? I didn't care about these numbers, right? So that's the second. Remember, all of these questions have two solutions, right? And those two solutions are a little bit different. They are essentially the same thing, but a little bit different, right? So here, in this solution, I don't care about, alpha. I calculate my t. I come into the table and so I come to the table and I find my t, right? Say, the t is between these two guys, therefore my probability is between these two guys, right? And this is less than point. Oh, actually, I think that these numbers that I put are, I have to put them, I have to move right? Yeah, I made a mistake. So I have to interchange the location of these two guys. What I wrote is actually incorrect, right? Because this guy is actually smaller than this guy.
Bigger.
But bigger. Yeah, sorry. But it doesn't matter.
Yeah, so in this case, it's not greater than or equal to, so you still, is your 0.1, yeah, what would you say?
Yeah, so basically for alpha equal to 0.01, we fail. Did I make a mistake? Yeah, it is still less. Actually, no, we still reject the null hypothesis. Even for 1%, we reject H0, right? Because the only mistake I made here, unfortunately, I can't delete this thing. Maybe I can do this and I can do this. Okay, so my p-value, which is alpha, is going to be between 0.01 and 0.005, and these two numbers come from here, right? It's between those two. Since it's very small, we reject H0, right? And we reject it, so if alpha is 0.01 or alpha is 0.05, in both cases we reject because our p-value is less than both of them. Right? The other solution where you look at, the t of alpha divided by 2 is a little bit different. So we do this and do this again. Okay. So in the other solution, after we calculate t, right, at this point, I will say, okay, now I will compute t of, so it's one-sided, so t of alpha and n minus 1 and 9, which is t of 0.05 and 9, right? And this t from the table is 0.05 and 9 is 1.83, right? And I say that, okay, my rejection range is from 1.83 plus minus 1.83, right? And the t that I computed is actually 3, is much, much larger than this. It's around here. So because of this, we reject the null hypothesis. Right? I personally like the other solution that is here more, where we calculate the p-value, right? Because here we just say we reject H0, but we don't really know what's the p-value, right? With the other solution, we also get the p-value. Yeah.
The sign doesn't matter. Like when you calculate t0 got -3, the sign doesn't matter because it's symmetric.
Yeah, it doesn't matter. The sign doesn't matter.
So in the table, we can search for the value of 3.
Yeah. Another thing that is might be confusing to you, I didn't mention it. So these, tables 4 and 2, the conventions are different for these tables, right? So here, Z, basically the phi of Z is area under the curve from -infinity to that Z. But here, area under the t distribution is the other way around. It's from +infinity to that value, right? So, that's the other difference between these two tables. And that's basically the reason that the book is written like this, because that's the convention of between the t distribution and the normal distribution, right? But essentially, it doesn't matter, right? So you can convert all of these numbers. So these numbers that you see, they're all positive, right? But for the normal distribution, all of these numbers are negative, right? But it doesn't matter because both of these distributions are symmetric, right? So it doesn't matter how you define this area, from +infinity or from -infinity. Okay. Perhaps we can do one more. Let me see what's the next question. Okay, so yeah, we can do this one. This one's easy. So a new engine manufacturing technology is proposed for reducing the pollution. 10 engines are sampled, and average and standard deviation of pollutions are actually. We should do this one. So this is exactly the same question as the previous question, right? But what we want to do here is to calculate the confidence interval, right? Instead of doing hypothesis testing for the same question, we want to calculate the confidence interval, right? We want to find 95% confidence interval for mu, right? And remember that the confidence interval is for mu, not for x bar, right? So this interval is for mu, because x bar is a value that we have, is 17.17, right? So how do we find this? It's actually exactly the same as the procedure that we did before. We have to use basically this equation, and here we have to use T of alpha divided by 2. So we have S is 2.98, N is 10, and the only thing we have to compute is this number, and this number, I think we have it in the table. So for 9 and 0.025, T is 2.26, right? So T of alpha divided by 2 and 9 is, what was it, 2.26. Right? So then we have mu is more than, can somebody please compute this quantity? So it's, the quantity is 2.26 times S, which is 2.98 divided by square root of 10. 2.13. So this is, mu is more than x bar, which is 17.17 minus 2.13 and less than 17.17 plus 2.13, right? So this will be right? So this will be some other numbers, right? So 15.04, right? So when we compute the confidence interval, we see that 20 is not in this confidence interval, right? So the minimum value is 15, the maximum value is 19, right? So this means that with a probability of 95%, mu is somewhere here, right? So it's a similar conclusion to the previous slide where we did the hypothesis testing, right? Here we don't test the hypothesis, we just calculate the confidence interval, but we see from these results that, you know, mu is likely not 20. Any questions? Okay, so what we do, you know, next week is we continue solving questions like this one. There's actually a few questions that are incorrect in the slides, in the solution manual, for example, 831. So I try to solve the ones that the solutions are incorrect in the solution manual. So see you guys next week.